Can you hear me? Very good. Okay, hi everyone. I am one of the PyData organizers, as you can see from my t-shirt. Welcome to the PyData April Meetup, who is very kindly sponsored by eBay. We have two speakers, Dr. Florian Wilhelm, who is here, and Ulrike Thalheim, who is sitting in the front row. This is us. So PyData Berlin, if you want to tweet at us, the slides, so these intro slides and the speaker slides will all be up on this GitHub page. So you don't need to record the links that I'm going to flash at you. You can just go here and see what the links are. PyData, who's here for the first time? Almost half, okay. So PyData, we're a worldwide community of meetups. We're sort of globally coordinated by NumFocus, who sponsors open source software development for scientific purposes. So Python packages like NumPy, SciPy, scikit-learn, Pandas, Jupyter notebooks, and so on. They're all sponsored by NumFocus and sort of implicitly, therefore, by us. And the point of these meetups is to bring together the people who use these tools and the people who develop these tools and get them talking and so on, sharing their experiences. London is the largest and Berlin is currently the fourth largest in the world. We've been growing at a fairly healthy rate. A couple of news issues. So we're organizing a conference. The conference itself is beginning of July. The call for proposals is currently open. The deadline is Sunday this week. If you are interested in speaking, you need to go to this address and submit a proposal. If you are a first-time, so for the conference we have three very good keynote speakers. Barbara Planck, who is an associate professor of NLP from Groningen. Toby Walsh, who is at TU Berlin, professor of AI, and Veronica Valeros, who is a hacker and works for Cisco on network intrusion detection, I think. Other news. There we go, this is what I want to say. So, if you are a first-time speaker, we are very open to having you at PyData. We want to draw in new speakers. If you're a little bit unsure how to put together an abstract, whether your talk idea is good, whether you'll pull through the talk, we have a mentoring event this Saturday, which is one day before the CFP deadline, notes, where you can come and talk to the organizers. There's going to be a couple of the organizers there, including myself, and Catherine, if you know her, and some other experienced talkers, speakers, who can help you with the abstract. They can help you with the presentation or the idea, whatever it might be. We'll also be at the conference, so you get a little bit of support from us at the conference as well. As I said, conference is in July. Ticket sales are also open. If you don't want to come, if you don't want to talk, but you just want to come see the talks, please do so. All set. Other news. Jupyter Notebook version 5 has been released. Who saw this? One person. Okay. This is important. So, version 5. You can now sort the notebooks by when they were last edited. You can also, your tables will go from looking like this to looking like this. And there's a fantastic, when you hover, so these are actually two different colors, but you can't see it on the screen. So when you hover over, you get a little highlight as well. It's pretty, and it works so much better than the previous one. So if you haven't yet, please update to Notebook version 5. Tagesspiegel is organizing a conference in May. Have a look at the link. the program is very interesting, but the tickets are super expensive. If you have a company who's paying for you, or you qualify for the what is it called? They have a program for digital future. There we go. They have a scholarship which gets you free into the conference. So you might want to have a look at this and see the scholarships. What else is happening? There's a Python Berlin Slack team organized by Dinu, who is here. There's also a Berlin machine learning Slack, which is now a couple of weeks old, organized by Abhishek, who I think I saw come in as well. Yeah, there is. So if you want to chat about Python or machine learning or anything related, this is the place where you want to go. PyData Berlin probably won't add a third. I think 2 is plenty. Okay, thank you all for coming. And thank you very much for, not mobile, thank you very much for eBay for sponsoring us. And again, we are PyData Berlin, and that's the repository where the GitHub slides are.
Hello, my name is Daniela, and this is the sponsoring talk. No. So I work for mobile.de. We are sponsoring this event because we have, since a couple of years, heavily invested in data. We now have our own data team. I'm not a recruiter, I'm actually a data scientist and a project manager. So if you would like to know what it's like to work at Mobile or eBay Tech, you can talk to me. You can also talk to Florian or Moritz, who's sitting in the first row if you're interested. I would be happy.
Welcome to my talk, Causality and Propensity Score Method. Thanks for the invitation tonight. So a few words about me, how I got into the business of data science. So I studied mathematics at the Karlsruhe Institute of Technology, where I also did some research in climate simulations. Then I became a data scientist at Blue Yonder. Has any one of you heard of Blue Yonder? Actually a few hands rising. Yeah, that's like the leading provider of machine learning solutions for retail. So mostly was concerned with how many goods supermarkets should keep in stock and what the future demand was. Then I changed to Innovex. This is an IT project house focusing on digital transformation, and there I've been working now for more than a year at Mobile, daughter company of eBay, in the really awesome data team. And so here I'm going to present a little bit what we are currently focusing on. So a small outline of the talk. I'll give a little motivation why we're going to focus on causation and causality. Also a little theory, of course. So what is the math behind all this? Then I'll give some examples, like the application in Python and scikit-learn, and some results. And of course, at the end, there's going to be some time for question and answer. So, but before we dive into, has any one of you read the book Big Data of Schönborn? Maybe, so no one. This was quite hyped like 3 or 4 years ago, and they had some quite bold propositions in the book. So one was that correlation trumps causation, and there were other quotes like society will need to shed some of obsession for causality in exchange for simple correlation, not knowing why, but only knowing what. And yeah, I think this book really kind of pushed it to the limits, because actually in many cases you want to know what's going on. So I think this is pure exaggeration, and yeah, so maybe if you haven't read the book, I think there's no real reason to do so. So since I just said that causality actually matters, the natural question is, of course, where does it matter? And one point where it does matter, for instance, at Mobile, is if you are a dealer and if you want to sell your car, then at Mobile you have options like additional commercial features. You can, for instance, buy this top of the page feature, or you can buy this red pencil, or somehow buy additional features that attracts more focus and more demand from the users. And of course, as a dealer, you are interested in how much am I really gaining. I mean, I'm paying for this feature, and so I want to know what the effect is if I buy this. So what is the average selling time maybe going down, or can I somehow buy or sell my car at a higher price? And due to the transparency, Mobile is actually looking right now into and evaluating into how one can present this better to the dealers, the actual effect of buying a feature. Another example is advertisement campaigns. So I once had a project at another company with advertisement campaigns, and if you're for instance in a marketing campaign and you have a budget and you want to use this budget to send coupons to your customers, then of course you're interested in sending those coupons to the customers who only gonna then buy something because they got the coupons. You're not gonna send them to maybe all the customers who gonna buy anyway, because then you're actually losing money. They're gonna use this coupon and get some discount. So you wanna give it to those who then really buy because they got the coupons. And so this is like the motivation. You see there are these are two good examples of where causation and causality is actually needed and why one is interested in looking into causation. So let's start to get a little bit deeper into what the actual causal effect is. So in machine learning, you quite often see this like feature matrices and a target vector. So how many of you have used scikit-learn? Okay, I see many hands going up. So this might be typical for you. You have your features and you have a target vector, and in supervised learning, you're trying to predict with the help of the features your target vector. So now I've added here one special feature, which I call the do feature. And this is the feature where we actually have control of. So this would be, in the example of Mobile, would be, am I gonna buy this additional top of the page feature, or am I not gonna buy it? So binary feature. And of course, the binary feature is then gonna affect the target. And so with y1, I'm gonna denote now the cases where the target is correlated, or where the target is in a sample where the do feature was set to 1, and y0 in the cases of 0. Because because in this cases, so we set the feature to 1, so we, for instance, bought this additional, and there's going to be some kind of result. And what we want to do now is the actual causal estimate the causal effect. So we want to kind of see how the target changes. And this is the causal effect is just a comparison of y1 and y0. Like you could compare it with a quotient or a difference, depending on if you would expect a multiplicative effect or an additive effect. And of course, the causal effect is just then the average between those two. And another notation that is quite often used is Pearl's do notation, which is the probability of y given do set. So again, we have this do feature, and set here is then the do feature or the treatments, it's also sometimes called, and this is just then the causal effect of set on y. So the distribution of y after setting the variable to some constant, in our cases 0 and 1. And already looking at this, we see that for each row we can either have a 1 or a 0, and this is directly gonna affect the targets. So we never have both, right? And this is the so-called fundamental problem in causation, that a causal claim is always a statement about what did not happen. So we either you booked the feature or you haven't booked the feature. And that means that the individual causal effect cannot really be measured. And another fundamental difference to machine learning is that, of course, correlation is not causation. You might know this comic of XKCD. And this is the problem we are dealing with, and this is what renders the problem not a typical supervised learning problem, because in a way we don't know our target. And yeah, this is an important thing to note and understand when you're dealing with causation, that you're trying to predict something that you don't really know, so it's not supervised learning. Another important topic where one is really interested in causation are, of course, clinical trials and studies. And there one has two different kinds of trials. First of all, there's the randomized trial. So this is like the gold standard trial that it's used whenever possible. So we have a treatment assignment set which is just completely random. You have your treatment group, your control group, and who's in which group you just randomly assign all your patients and volunteers that showed up. So set is completely controllable, and this is like, yeah, this is the gold standard. But in some cases we have observational trials. Let's imagine for something that you want to do some kind of studies on cancer patients, and like giving a placebo or something to a patient with cancer would be kind of unethical. So in some cases you only have data from observational trials. So this is the case. In this case, your treatment variable set is not really controllable, and also this means that your treatment assignment is somehow going to depend on X. And these are the interesting, actually interesting cases. For instance, with the use case of mobile, it might be that dealers selling expensive cars like Porsche or something are more inclined to also spend more monies on additional features. So there's going to be a correlation of the car and if there's going to be something booked. So it's not going to be a randomized trial in our use case. And we look into both cases, yeah. And the problem really is in this observational trial, because we have then this correlation with other covariates X, so with other features, and this gets us in the danger zone. So before we go on, there's one important definition that I actually want to show, a kind of basic assumption that we need to take when we are dealing with causality, and also in the complete rest of the slides and of these talks. And it's a so-called strongly ignorable. So again, we have our X, the covariates. We have Y0 and Y1, the potential outcomes if you get the treatment or if you're in the control group, so if you don't get the treatment. And we say that the treatment assignment is strongly ignorable given X if the potential outcome is independent to the treatment assignment set given X. So one has to take a minute to think about this. So what this actually means, this means that if I really know everything, if I really know everything about my patient, and then I look and then I condition this on Z, then this is completely independent of the potential outcome. So this is the assumption we're going to have to do. It could also be, in some cases, it could be that someone, for instance, chose the medication based on some genetic markers or something, and if you don't know this, and if it's not in X, then this assumption is actually violated, and it's it's not really possible to check, but this assumption do we need to take. And also that the probability of being assigned to the actual treatment group is neither 0 nor 1. So there's a chance to be in either groups. This is another. And so this definition of strongly ignorable is from the original paper. And another definition is of Pearl, of his causality book. And he says if we assume this, we are basically making the assumption that X is what he calls admissible. And admissible means that the probability of Y given do Z is just this marginalization, so the sum over the probability of Y given X and Z times probability X. So this is basically, it's the same assumption, and one should always be aware that when you're dealing with causality, this assumption needs to hold, otherwise you're going to get wrong results. So we assume now this works for us. And how would we now deal with causal effect in a randomized trial? So randomized trial, again, like the easy case. So if you want to use machine learning for this, we can basically make a really simple approach, like maybe everyone would do. We just train a model with the covariates X and Z as features and Y as the target. And then we can predict, given an X, the response Y hat 1, by setting this do feature to Z equals 1 and Z equals 2, and calculate the effect. And we'll later see in the example that the actual results are going to be quite good for doing so. So in the case of a completely randomized trial. Okay, but what happens now if we are dealing with observational data? What if the do feature is highly correlated with other features? And there we're going to have the problem that we somehow need a way to isolate the causal effect from all these other features to kind of show our machine learning method. Maybe we're using a random forest or something like this, how we gonna kind of present this in a better way to our machine learning method. And yeah, the method I'm going to present here is the so-called inverse probability of treatment weighting method. It's a propensity score method. So what is the propensity? It's the propensity of receiving the treatment. So mathematically, the propensity score is therefore just defined as the probability of receiving the treatment given my feature vector. So that's the propensity. And if we use a machine learning method, maybe something from scikit-learn, we can just easily calculate this. We just need some kind of classification method which returns class probabilities. There is, in most cases of scikit-learn, you have this predict underscore probar method where you get then the probabilities. And yeah, you can even adjust them. So based on these propensity score methods, we're gonna then define some weights. And these weights actually give weight to our different samples. And the basic idea is that we want to give a high weight to a sample which was actually set in a way that we least expected it. So if we just look at the first term now and say that the treatment was 1 in our example, but using this estimation method, we actually thought that this patient is not going to get a treatment, then the weight will be high, because this is going to be small, so we give it a huge weight. And with the second term, it's just the other way around. We also assign huge weights where the actual assignment was least expected. And this is, by this we are therefore generating a kind of synthetic samples. And those synthetic samples, the treatment is no longer so strongly correlated to X. So the idea or the intuition behind it is that we are kind of showing like, hey, look at these samples. There something happened which is really unexpected, and by this we are changing that. And I will later show this in the samples in an example how the correlation matrix changes by using this. So if we have those weights now, how would we proceed in a non-randomized trial, so in an observational study? We would again, we would train a model with the covariates X in order to predict Z. Then we would calculate the propensity scores and to get the weights. Then we would use a second model to train the covariates X with the covariates x and z as features and the response y as target, and use those weights as sample weights. And then we can just do as we did before, like setting to 0 and 1 and then comparing the results. So to actually demonstrate this, I created a synthetic example. So why not take any real data? Again, we have the problem that the fundamental problem of causation, that I mean, for real data we don't know the causality, so one way to overcome this is just coming up with an example where you know the actual causality, the effect, and now we try to use the data generated by this example to see if the method kind of finds out the effect or finds the effect that we actually put into this example. So to generate the data, I take a Poisson distribution and the expectancy value of the recovery time. So again, we are in the field of clinical trials. The recovery time is e to the power of 2 plus some indicator if you're male, so the gender is important, and then your age and the severity of the disease. And if you take a medication, then this is going to be reduced by -1. So since it's e to the power of -1, there's going to be a multiplicative effect. And if you take the medication, your expected recovery time is going to reduce to 37%. So now we have this formula to generate the data. And we need now some distributions for the gender and the age and the severity. And here I just took a uniform distribution, like 50% on average, 50% male and female, and a gamma distribution with some shape parameters for the age and the severity, beta distribution, so that we have it between 0 and 1, so almost. So no severity, 0 and 1, like the highest impact the sickness or the illness can have on you. Okay, maybe just because no one can actually imagine those shape parameters, how does this look like? So for the age, this is a density plot, so a histogram over the years. So we see that many of our patients are around 30 years, between 20 and 40. And the severity distribution looks like this. And using those, I just then generated 10,000 examples. And now that we have some data we can actually work with, we need to also assign the treatment. There are now 2 setups that we're going to look at. First of all, the randomized trial. So what happens if I really just by chance now take those patients I created and just say, okay, with a chance of 50-50, you're going to be in the control group or you're going to be in the treatment group, and then use a Poisson regression. So that's a parametric regression with a strong assumption about the underlying distributions, or just some random machine learning method, the random forest. And the second setup will be, what if I do the assignment now based on X? So later I'm going to show how I did this assignment. And then again, use the Poisson regression and the random forest just to see how this works out. So first of all, just to check again the correlation matrix in the randomized trial. And by definition, I mean, we just said we randomly going to assign it. We see there's no correlation between medication and the gender or age or severity. So this is completely as expected. So what happens if we now use this data and use the Poisson regression? Poisson regression I used from stats models. And we see that the actual coefficients are correctly estimated. So coefficient of the gender was 0.5 and 0.03 and so on. And also this would be the causal effect we are interested in. And Poisson regression as expected. I mean, we generated data with the help of a Poisson model, and now we are estimating again. So yeah, it would be rather uncommon if not exactly the same turns out as we put in. Okay, so this worked fine. Again, what happens if we used a random forest? And here I used a random forest to predict, just like in the method I explained. So I did train the model, I set it to 1 and to 0 and divided one by the other, so y1 divided by y0, and made this histogram. So we see that the real treatment effect is here, and the average treatment effect of our patients is really close. So it's actually just using machine learning got us a good estimation of the true average effect. For the individual average, for the causal effect. For the individual causal effect, there's quite a spread, but most of it are close. So even for the actual patients where the causal effect is also 0.37, we are really close. So it's still, we have a kind of decent estimation in this case. So what happens now with the non-randomized trial? So yeah, let's just assume that somehow men complain more, and all know maybe the man flu or something. So let's assume men complain more and they're more likely to receive treatments because they kind of argue with their physician to get the medication. So we take this indicator variable of the gender plus the severity. Of course, also if you're more severely affected by this sickness, you're also more likely to get the treatment, and also plus some random term. And if this is larger than 0.8, then you get the treatment. Otherwise, you don't get the treatment. And this is just something that I came up with. And important thing is that if you're male and if you have the sickness we're talking about more severely, then you're more likely to get the treatment. So if we now look at the correlation matrix, it's again like expected. We have now a strong correlation between the gender, to the medication. And also the severity is now actually influencing this. So now let's again check what happens if we take the Poisson regression. And yeah, we still see the estimations are, the inference is really good. So we have again the 0.5, the 0.03 severity was 2 before and is still really close to 2. And what we were actually interested in, or are interested in, the medication is still correctly estimated. So one could wonder, okay, why now is this still working? And the reason for this is that we have a strong model dependence. So this is because we generated data with the help of a Poisson model, and now we are fitting again with the help of a Poisson model. But with real data, this would not work. So in this case, it works in our favor. But if we had like real-world data where the underlying dynamics are not as we expected are not as expected, then of course we would get a result, but the result could largely, could be actually be different to what we are estimating. So in most cases, model dependence is something that we don't want, and here it works in our favor. So the interesting case is actually the random forest in this now, the non-randomized trial. And we see here that the average causal effect is quite off. And if we look at the individual effects, we see that we even have another mode here. So this will be the women, for instance, women that don't have this sickness that we're talking about, which have it not so severe. And in this case, for them, the random forest thought, okay, it's rather important that you're a female and this habit and the severity is low compared to taking the medication. So, and this is why we're seeing this wrong result if we just take a naive approach and just use the random forest as before in the example with the randomized trial. So I just applied it the same way as before, but with this non-randomized trial. So we see that the effects is actually highly underestimated, because this is a multiplicative, so highly underestimated if it's to the right. So now we do this, what we said before, we calculate the propensity score. And here just made a plot of the propensity score. We see that, we see different propensity scores. Those will again be the females, where we know that if the severity is also low, the chance of not getting the treatment is quite high. And on the right side will be, for instance, the man again, that and more severely affected patients where we know, okay, the chance of getting the treatment is quite high by this assignment we have chosen. So if we apply this to the correlation matrix, as I said before, the correlation is gonna decrease a lot. So here again, I showed with no weighting. So this is the correlation matrix that we saw before. And with weighting, we see that the correlation goes down. So I took the sample weights coming from the propensity score and used a so-called weighted correlation matrix. So the correlation of this kind of synthetic samples that I graded, there the medication is far less correlated with the medication and the severity as before. So this is already a cool result that one can, by like changing the weights, kind of eliminate the correlation. Just for comparison, what would have happened if we've calculated propensity score for the randomized trial? Just wanted to check it if everything is all right. And we see that the probability is for all patients really close to 1/2, because yeah, it was random and we chose 1/2 to be the assignment probability for treatment versus control. So if we now use those weights with a random forest, and then we get this result, we see that the mean still is, the average causal effect still is underestimated, but we are much closer to the true mean. We again have some unimode distribution, so it's not that we have this this second mode anymore. The only downside is that we have a few outliers. So beforehand we had not, we did not have any patients with a extremely unrealistic medication effect of more than 1. But overall, we improved our estimation of the average causal effect, and also for many of the individual patients. One can also see this again if you do the comparison. So the blue one was of our first setup, so the randomized trial, just using a random forest, and the non-randomized trial, just applying it the same way as before. But yeah, for the non-randomized trial, this is the green one, where we see this this wrong estimate with a lot of wrong estimations, and then the non-randomized trial with the help of the inverse probability of treatment weighting. And there you can see that it improved a lot, but of course it's still not as good as if we had done a randomized trial. So this remains to be the gold standard, and whenever you got the chance to do it, whenever you are in control of your treatment, then you should do it. So to come to a conclusion, we saw this, that inverse probability of treatment weighting improved it, and it's in this case, and whenever you have the chance to apply it. It's better in an observational effect to do it compared to a naive approach. Of course, there's some counter examples where it could be the other way, like it's like in many cases. But in general and in realistic cases, it makes sense to look at propensity score methods if you are dealing with a problem in the domain of causality. We also saw what's really interesting, that if you postulate a model like a Poisson regression, some parametric model where you make certain assumption about the dynamics, about the distributions, then you will also get a result. And if you're lucky and the kind of model you're postulating really is similar to the actual dynamics that created the data, then you will also get good results. But of course, it's a bold assumption. So this is always the case when you're dealing with like more stats point of view, like making an assumption about your distribution, or if you're going more down the machine learning road and just say, okay, I take some nonparametric methods and I just see what comes out. So randomized trials remain the gold standard, and in some cases you can also do it, like typical would be an A/B test that you can use for some things. It would be hard if you would do this for all the vehicles, and if you have this strong correlation with the car, for instance, on mobile.de. But if there's a possibility to do an A/B test, then of course this is preferred. And further improvements. So what I did in this example, I really just used out of the box random forest. You can do further improvements, like you could also start doing some kind of residual training and further improve this. So this was just like a really simple example to keep it simple. So if you got interested in this topic, here are some references, and as said before, you're going to see the slides and can look at this. There's also a blog post about this where you can also download the Jupyter notebook, not in version 5, but it's independent of the version anyway, I think. So where you can download the Jupyter notebook and play around with all the plots I created and these synthetic examples, where you can just play around with it. Okay, so thanks a lot for your attention, and I'm open for questions.
Hi. Is it? All right. Okay. Thank you very much for the talk. It was very clear and very nice. I just wondered if you could speak to how you calculated the propensity scores in this study. Do you calculate them directly, or were you using a model for that, a machine learning model, like a regression model or something?
Yeah, I used logistic regression. So I also wanted to use something from scikit-learn, and since it's a classification method, then you know what happened if someone got or didn't get the treatment, and then logistic regression is always good because you already get quite good estimations of your class probabilities. If you want to use a random forest or something, one needs to be careful, because the class probabilities are not going to be adjusted, but there's also a meta estimator in scikit-learn that you can then use to calibrate. The better word is calibrate, to calibrate the class probabilities to your actual distribution. And if you want to look in this notebook, it will be there. And there I had this once done in logistic regression and once with another classifier that I chose, and this calibration.
Did you try to use log transformation before applying random forest?
Log transformation.
Yeah, and see how it performs compared to the normal random forest. Log transformation on the observations.
No, in this case I haven't done it. No.
Because then it will be similar to the Poisson model.
Yeah, actually, yeah. In this case, yeah, I took this. Took this quotient, and yeah, if I took the log transformation, then I could have looked at the difference, and yeah, the good point, yeah.
Well, then let's have a little 10-minute break, and then for our next speaker. Okay, please welcome our second speaker, Ulrike Thalheim, who is going to be talking about open data use cases.
I'm Ulrike Thalheim. I'm a co-lab lead of the Berlin OK Lab. OK Lab stands for Open Knowledge Lab, and it's one of 26 labs within the Code for Germany environment all over Germany. A few words about myself. I study political sciences in Constance, Warsaw, and Barcelona with a very quantitative focus. So I did a lot of statistics, also used propensity score calculations for my master thesis. So Florian's talk was quite interesting to me. And after I finished my studies, I was looking around what I could do in my spare time while looking for a job, and I ended up in Berlin's open data community because back then the Berlin OK Lab was just founding itself. So yeah, I kind of joined this movement. I have been staying on it since then, so since 2014. I also earn money. I work at iWhite. It's a German digital NGO, and I work on a project on enhancing digital information for refugees on consumer protection. And I also have a job at a market research company here in Berlin called FactWorks. So a quick look on the agenda. I will do a quick introduction into what the OK Lab is about and what open data is about. Then I will go on into 4 examples that are quite interesting and really current examples of Germany's open data community. And then at the end I will also tell you how you can get involved. So let's start with the OK Lab. As I said, OK stands for Open Knowledge. We are a big community here in Berlin. We meet weekly, every Monday at the Wikimedia offices near Möckernbrücke. Once a month we have open labs where we welcome you, interested people, and we consider ourselves rather as a co-working space for open data and civic tech projects. So we don't have that one big project, but everyone is kind of working on their own projects, and we exchange thoughts, present our stuff to each other, and from time to time something really interesting comes up. Last year, for example, we had a focus on digital on fostering and supporting digital solutions for refugees and migrants and integration. I for myself have been working in a project on a project database for refugee and integration projects. So before we continue getting into the examples, just a very quick definition what open data actually means. So we do have open data when there's open data and content that can be freely used, that can be shared, that can be modified by anyone for any purpose. So without restrictions, under free license. I would also add in a machine readable file, because a lot of times people publish PDFs and say, okay, that's open. Well, PDFs are quite hard to handle, especially if you have tabular data. That can be quite a mess. So we would like to have open data also in machine readable forms. And who is publishing open data? So of course this can be administrations, the government, but it can also be science. A lot of scientists publish and also use open data. It can be businesses, foundation, and so on, public institutions. Yeah. So that's it, and now let's dig into the examples. So the first thing I would like to show you is measuring air quality. Air quality is quite basic and quite important for our life quality. If the air is bad, it's quite harmful for our health, right? It can produce lung cancer, asthma quotes rise up, and so on. So the public and also public institutions are interested to keep the air quality good. And how to do that? Well, you have to monitor it and you measure it. So the Umweltbundesamt, the German agency for that, is measuring it in different points and reporting it. And that would be the PM10 value. I don't know if you can read it. Just brought it if anyone wants to look it up again. The PM10 value is the value that measures Feinstaub, fine dust, small particulates with a diameter of 2.5 to 10 micrometers. That's really like small particles. And like I said, they're not really good for your health. The European Union has defined a standard or kind of like restrictions on what should not be exceeded when it comes to air quality. So for example, a city jurisdiction should not exceed a yearly average of 40 micrograms per cubic meter. Furthermore, a city jurisdiction should not exceed a daily average of 50 microgram per cubic meter. However, there's an exception that you can have up to 35 days with that exceeding daily weight. And in Berlin, we're quite fine with it. This is on the worst street, which is Silbersteinstraße, and also Frankfurter Allee. Silbersteinstraße is in Neukölln. There were 18 days last year, so it wasn't that bad. The year before was a bit worse. It also really depends on weather and furthermore. And fine dust is well produced by vehicles, but if it rains a lot, the dust comes down and it's not in the air. But there's also a city called Stuttgart in Germany. Many of you might know it. It's it's situated in a vessel, and furthermore, there's a lot of car industry in there. A lot of people really drive cars, while we have a lot of public transport being used here in Berlin. And they had 58 days last year with these exceeding PM10 values, so it's more than 35. So the city should do something about it, but we're not really doing it. I'm sometimes thinking about restricting traffic, but not. Well, the car industry is around, so it's really hard to do that. So the OK Lab in Stuttgart said, okay, we have to do something. We have to improve the measurement system first, and then we can put up some pressure on the institutions there. So what they did is inventing a really small sensor set that everyone can install on their balcony. This is the sensor of the OK Lab in Stuttgart. You can buy it. You can buy the set parts of a set on your own at Alibaba in China. There's a list in the internet where to buy it. All of the components together cost around 35 euros, so it's quite achievable. It also comes with a Wi-Fi chip, so you can connect it to the internet, and it sends the data back to Code for Stuttgart, so they can really make a big map about air quality, and it measures about, like, I think every 15 minutes. So I also have one on my balcony, and well, okay, the OK Lab Stuttgart has this nice map, and this is a screenshot from January, where there weren't that many sensors out yet. However, in January the situation was quite bad, so it should be green. Green would mean it's below 50. Well, it was kind of red and violet, so it was above 100, 200, and so on. Quite bad air quality. And visualizations like that are really, really helpful to make the public aware of the situation. Well, of course, alarming colors. The Umweltbundesamt would not do it that way. And furthermore, to put more pressure on institutions to actually do it. So it's also a political message behind it. And we can just look up the map right now. So that's it right now. A lot more sensors got into as well, because it's a project that got really well received also by the press, and more people are interested in buying sensors and put them on the balconies. Here we have a cluster of Berlin and surroundings, so we have 15 sensors, and right now we have a mean of 7, so really below 50. So right now the air quality in Berlin is quite good. So let's go to the next project that's quite interesting and widely discussed in the open data community. Well, we have elections coming up. We also had an election in Saarland a few weeks ago, and in Nordrhein-Westphalia and in in Schleswig-Holstein there will be elections in May, and then in September we have federal elections. Before an election, citizens usually would like to inform themselves. However, well, they can do it in the press. When it comes to elections, they could also have a look on what the government and what public institutions offer. And we have statistische Landesämter, Bundesämter, so statistic agencies in Germany, also federally organized. However, they're many times not offering what citizens really need, like really easy, comprehensible visualizations. Furthermore, it's sometimes really hard to find the information, for example, on how to vote. And we at the whole Code for Germany community would like to improve the situation. So just to give you a short example of what I was talking about, this is how they present, well, hard to see here, but this is how they presented the results for the Saarland election in March. Well, there's some very easy visualizations, but for example, there's no download button. You can't easily download the spreadsheet, so this is not open. It's also really hard to see how they voted, what rules applied, and so on. So that's a really bad example about how to present election data also in the aftermath, but usually we are also talking about election data before an election. So what Code for Germany actually did is the office at the Open Knowledge Foundation, where actually people are working on it, and not like me doing it in my spare time, got funding by Google, and we will start a project called Wahldaten during the next weeks and months, where we try to make more data sets available. We will really try to get all different interest groups into one room on several occasions to talk about, with, of course, the agencies, but also with data journalists, with activist groups like, for example, Abgeordnetenwatch, with scientists, with a lot of electoral scientists, and of course coders and the open data community. We would like to spotlight the issues of the websites of the agencies, like I showed you just around, and also show best practices, because there are some good offerings as well. But of course, we also have this federal system. It's sometimes really hard to do. Then in the end also develop some apps, because, well, you can always ask for more data, but you also have to use it. And there's some really nice applications that come into my mind. So please follow Code for Germany to keep you updated on this. And I'm pretty sure we will have some really nice things coming up during the next months. So next project is Wikidata. I just talked to Matti. Matti told me he has been using it for a few months or weeks now as well. Weeks. Okay, so I don't know who has heard about Wikidata. Okay, phew, well, that's pretty cool. So here I have a screenshot of a Berlin website on Wikipedia. It offers some information, and here on the left side of a menu, you also find a little small button saying Wikidata Datenobjekt, so Wikidata data object. When you click on it, you will come to a website or to a site of Wikidata on the object of Berlin. And on the right side, for example, you will find, I can also just go into it and maybe it takes a while until it loads up. It's much bigger, that's great. Yeah, this website is pretty large, and it contains a lot of information about Berlin, such as describing it, it's a city-state, it's an integrated municipality, a city, and so on. Pretty much big relational data set on Berlin. And what I'm missing, well, a really nice use case is this one. Here you have all the translations of Berlin in different languages. So why is this useful, and why did Wikipedia come up with this new project called Wikidata? All of these information were kind of collected by individuals during the last 15 years, 20 years, since Wikipedia runs. And whenever it was a different language, information was typed in newly. Now everything is linked. So if one page gets updated, so for example the German website on Berlin changing the name of the mayor, this will also be updated in other versions, the language versions. So that's a really, really useful thing of Wikidata for the Wikipedia. But Wikidata becomes kind of a project of its own now as well, because it's just a big database, growing, community-driven, and quite useful. There's a query service you can use. It's a bit messy in the beginning. Well, it's Sparkle. It's not like the most prettiest query language to use. But in the end, you can build up your own data sets out of a big database. And query, for example, was a screenshot of female mayors in big cities. Query a big data set, get a list, or table, rather I say. And for example, you can download it. You can also integrate it via an API. You can display it, visualize it, so it's also usable for people who are not that well into coding and are not that well into coding and programming. And this database refreshes, so that's really, really useful. You can also build new applications on it. So for example, a friend of mine at Code for Berlin built up a small application called Stadt, Land, Fluss, or there's Inventare, which I think is really, really nice. Let me just show you this. Loads a bit. This is a place where you can catalog your books, and of course a lot of books are also stored in Wikipedia, and that means Wikidata. It's proposing you books and so on, and we're using the big Wikidata database that is growing and growing. So that's a really nice example of Wikidata. And so what you can do as a community, of course it's all open, is using it, putting in new entries, querying all that stuff, and linking data as well to wiki media entries. So, wait a second. Okay, so my last example I brought with me is rather small one, but really nice one on activism as well. So I told you about the measuring air quality project, which is kind of also showing the activist side, and public transport data also needs a bit activism. We see some activism by the open data community in Germany currently. So whenever you, here in Berlin, we use a lot of public transport, and we look up the schedules either on the BVG website or on Google Maps, but there are no more services. Well, maybe Bahn.de, but others were not. And the case behind it is that the public transport associations do not really open up the data. They sometimes share, or they share it usually with Google in a web or in a commonly agreed format called GTFS. But they don't share it with the public. Well, they're PDFs, they have their own website, but they don't open it up. Why do they not open it up? Well, lazy, haven't thought about it, also kind of like, we have to put in more effort, why? They don't really see the use cases. Well, there's actually a lot of economic potential behind it. Of course, there's Google. Google is a big company, but there could be more companies being really interested in this public transport data, building new applications on it, for example, combining more and more transport means with each other. Also looking more and more how they can solve issues better than the current applications. So what a few friends of mine thought what would be nice is to put up a website where you can type in your zip code. You have a little form where you type in a bit of your information, and then a PDF gets generated with a little letter you can send to your public transport association and ask them to open up their data. Of course, this is rather something for the open data community, but sometimes you really have to be obnoxious and ask for data, and not just one person, but a few more, to really show institutions like the public transport institutions, well, there are people out there being interested in the data, please open it up. And the result of this activity right now is that the people putting up this website, Rette dein Nahverkehr.de, so save your public transport, got a few responses by different public transport associations, actually considering now opening it up, putting it into discussion. So hopefully there will be more. Luckily here in Berlin, the BVG has been cooperating, opening up the data since I think 2012. So they were the first ones. Berlin and Brandenburg opens up its data, and I think, for example, Ali app, I think many of you might know it, also uses this data. But well, as you can see on this map in Germany, there are just a few spots where this is happening right now. So that's a little activist side of it, also nice, where you get this semi-automated letter. Sometimes you have to be creative. So how to get involved? First of all, use the open data. Like I told, Wikidata is a great database for open data. Also, the air measurement project is putting up all the data, the Luftdaten, online, so you can use it also via an API, build your own bots and so on. Berlin has its own, the Berlin administration has its own website, datenberlin.de, where you can find lots of data sets on Berlin, and it will be more because last year Berlin got its new e-government law, and right now they're looking in how to implement this law really well. So there will be more data sets open, and also with a new administration, we're more interested in this topic. topic as well. Germany also has its own data portal, that's govdata.de, and currently the open data law in Germany is in the reading at the Bundestag. So I think within this year we will have also an open data law in Germany, so we will have more open data sets as well. You can come by at the OK Labs, of course. Here in Berlin, as I said, we meet weekly and once a month. Next date will be May 8th, and then in June 12th we have our open labs where new people can come and we give a short introduction into open data, and not the way I did it right now, but more into what we really do here in Berlin, because these were examples rather throughout all Germany. And yeah, please come by. You can also ask for data. That's another project by the Open Knowledge Foundation, fragdenstaat.de, where you can ask by the Freedom of Information Act, get to your institutions by Freedom of Information Act and ask for information. That's something that journalists really like to use. And last but not least, here's my email. You can find me on Twitter via Code4BE and my personal handle didumdida, and I was really happy to use some open source software as well. Thanks a lot. Any questions? Yes.
If you are a poor foreigner like myself, are you also welcome to come to the OK Lab open data night if you don't speak German?
Yes. We usually try to speak English. As soon as someone comes speaking no German, we switch into English. You're very welcome. Yes?
How does the open data law work here? So if you knew the government had a particular data set, and I guess you have to be German, but if a German asked, do they have to provide it to you in a machine-readable form, for example?
Currently, it really depends by the states. So, for example, in Hamburg, they have a transparency law. So the public institutions really have to provide it, all the data, and I think in a machine-readable form as well. But we're not. That's the case. But right now with e-government, it really depends a bit. So it's always also a question of cooperation. But in the end, in Berlin, we got this e-government law last year, and we're right now discussing the implementation. But I'm pretty positive on the fact that they will try to publish as much data in a machine-readable form as possible. Of course, sometimes they only have their PDFs as well, that would be it. I think it's rather a question issue with federal agencies. The smaller it gets, the more collaborative the institutions usually also get.
Just a follow-up question, does PDF count as machine-readable? It's technically readable by a machine. Yeah, it's technically readable, but have you ever tried to convert a PDF containing tabular data? Not tabular data, but I have tried converting PDFs to more readable formats. It's not easy. Yeah, and that is even more accounting for tabular data. You can do it, but then you really have to compare everything. So is there any is that sort of recognized in the law that machine-readable formats actually mean, CSV and I don't know, SQL dumps and so on, or is it as long as it's electronic, it's machine-readable? I'm actually not totally sure about it. I will research it and will tell it on Twitter, and you can forward it via PyData if you want to. Thank you. Other questions? No more questions. Okay, so then let's thank the speaker and then